Now back to the quadrotor dynamics. The equations at the bottom tell us the net force and the net moment. If we combine the net force and the net moment with the Newton-Euler equations, we get these two sets of equations. On the right side, you see the total thrust, which is U1, and remember this thrust vector is known in the body fixed frame. The matrix R is rotating this thrust vector to an inertial frame. At the bottom you see the net moment, also known in the body fixed frame. But the equations as they've been written have components in the inertial frame on the top and in a body fixed frame at the bottom. These are the Newton-Euler equations, and these are the equations we'll use to develop controllers and planners for our vehicles. One question you can ask is how we actually calculate these parameters. Or in an online setting, how do we estimate these parameters? If you think carefully, the parameters you really need to know are those corresponding to the geometry, the length L, for example, and those corresponding to the physical properties, the mass m and the inertia I. You can also see that these parameters appear linearly in these equations. So if you had a system that allowed you to measure positions, velocities, and accelerations, it's actually not too hard to estimate the lengths, the masses, and the inertias. You should also verify that it's quite easy to calculate the angular velocity in the body fixed frame. If you know the pitch, roll, and yaw angles, and you know the rate of change of the pitch, roll, and yaw angles on the right side, a simple transformation yields the angular velocity components P, Q, and R along B1, B2, and B3. So this model is quite complicated. It involves three components of position, velocity, and acceleration, three components of rotations, angular velocities, and angular accelerations. To get a feel for the control problem, I'd like to first look at the planar version of this model. So we'll look at the equations of motion in the YZ plane. We will assume that the robot cannot move out of this plane. In other words, there's no motion in the x direction. And we'll also assume there is no yaw or pitch motions. As a result, we come up with the three equations that you see here. Equations that describe the rates of change of velocity in the y and the z direction, and the rate of change of the angular velocity in the roll direction. To describe these kinds of systems, it is useful to define a state vector. In the three-dimensional case, we have 6 variables that describe the configuration of a robot, and a state vector includes the configuration and its derivative. So if Q is the 6-dimensional configuration vector, Q and Q dot constitute a 12-dimensional description of the state. The space of all such state vectors is called the state space. If you look at the equilibrium configuration, and that configuration is defined by the position x0, y0, and z0, the configuration by definition also has a 0 roll angle and a 0 pitch angle. It could of course have any yaw angle. The equilibrium configuration must also correspond to 0 velocity. If I write it down in terms of a state space vector, you have the equilibrium configuration Q sub E, and you have a 0 velocity vector, and that gives you a 12-dimensional vector where the bottom 6 elements are all 0. Similarly, for planar quadrotors, you have a 3-dimensional configuration space, a six-dimensional state space, and an equilibrium configuration and an equilibrium state that can be similarly defined.